Depth cameras show a number of limitations during the capture of depth of transparent objects due to their specular effects, IR patterns passing through them, or reflections off shiny surfaces. We categorize prior approaches to complete or estimate these missing or corrupt depth values into two kinds: supervised depth completion methods, which are trained on ground truth depth information that must be acquired, and NeRF-based approaches that do per-scene estimation from multiple views. Our proposed method belongs to the latter. A notable work in the area was DEX-NeRF, which used NeRF to generate depth maps of high quality. However, it took significant time to process each scene, and the environment conditions had to be right. Recent advances in NeRF literature has improved reconstruction speed, but environment requirements are still prohibitive in real-world applications. Our method consists of three components to address specific issues. Firstly, NeRF capture view-dependent appearance of objects leading to inconsistent depth. We propose the use of semantic masks to guide surface density acquisition of transparent objects. By construction, radiance fields capture the appearance of the object without consideration of its true shape or depth. For transparent objects, as their appearance is dependent on the scene behind them, their density values are often distributed over a large distance. Semantic fields, however, capture semantic occupancy of the object in 3D. This leads to significant changes in density values near object boundaries. By jointly estimating both the radiance field and the semantic field, the resulting semantic radiance field is able to capture sharper object boundaries while still being able to use visual clues in RGB. Secondly, segmentation labels are difficult to obtain for rare transparent objects such as those used in laboratories. We propose a method for the grouping of label-less object segments obtained from VFMs into a set of non-overlapping masks. We use SAM and a relatively simple heuristic to group segments, output by SAM into layers or sets of non-overlapping masks. These segmentation masks are used to guide the semantic NeRF reconstruction process and overcome NeRF's limitations and allow us to obtain clearer, more coherent depth values. Thirdly, NeRFs are still quite resource-hungry in terms of time and number of views needed and suffer from a number of issues, including the infamous floaters. We propose some extensions to NeRF to tackle this. Specifically, we use an instant NGP base with a diffuse specular color split, an additional frequency position encoding, and both semantic and depth supervision. The addition of position encoding encourages reconstruction towards flatter surfaces, which are particularly important for smaller objects that are close to the table. To evaluate our method, we chose the ClearPose dataset for transparent object, which contains 63 objects, in a number of challenging configurations. We compare against Trans-CG and DREADS as supervised depth completion methods, and NeRFacto and Depth NeRFacto using Zoe depth as NeRF baselines. Our proposed method, SAID-NeRF, outperforms all methods on most of the test sets and offers a strong training-free alternative to depth completion. We find that SAID-NeRF generates sharper depths in comparison and is less prone to missing or overly smoothed values and doesn't struggle with issues of generalization. For the robotic grasping experiments, we use a Franca Imica Panda robot with a custom gripper that can adapt in the horizontal and vertical directions. For the data collection process, we place the transparent object in front of the robot and have it collect several images sampled from a hemisphere as visualized here. We choose 10 transparent objects for our robotic grasping experiments to span a wide range of shapes, sizes, and domains, including household objects and lab equipment. On visualization of the point clouds, we find that our method SAID-NeRF outputs denser, clearer outputs with fewer artifacts. Additionally, we also evaluate against GraspNeRF, a strong, recently proposed, transparent object grasping method, which does not operate off point clouds, so it is for visualization only. Our method, SAID-NeRF, outperforms the methods tested by a significant margin across all objects. We characterize the failure modes of the experiment into three kinds: slip failures, where minor inaccuracies cause slippage; push failures, where the finger collides or pushes the object out of the way; and air grasps, where failure is more significant and it attempts to grasp nothing. In summary, supervised methods for depth estimation require hard-to-acquire ground truth, but may still suffer generalization issues. NeRF are a promising training-free alternative, but are highly sensitive to views and are resource-hungry. To overcome this, we present a method that utilizes masks to guide the surface density of transparent objects, a heuristic for grouping, labelless segments obtained from SAM into non-overlapping masks and extensions that enable fast, robust, and reliable capture in several difficult scene conditions. We find that our method is remarkable under several difficult conditions and is a promising alternative to depth completion methods and for tasks such as robotic grasping of transparent objects.